there are a lot of pieces here. So if you'll recall the Atwood machines we did first semester, which felt like sometimes they could be pretty complicated, these are going to be like that, and they're going to be even more so, because we have to take into account what's happening to the wheel. I have to count on you remembering the stuff from first semester. So can we agree on a few things before we even get started? Like, assuming there's nothing holding the wheel in place, this system is going to accelerate. And that it clearly is going to have an acceleration kind of like that. So at the start of this problem, I'm going to make upwards positive on this side and downwards positive on this side. But now we have the wheel that's spinning. Now the wheel isn't changing location. I think we can agree, though, that the wheel has a pivot point at its center. Is that okay? I'm identifying the pivot point. We're going to need that because we're going to be talking about torque in a bit. And the wheel's rotational direction will be this way, which is going to make out of the page or out of the board the positive direction. So I'm saying a rotation that is out of the board is positive. Is all that okay? You understand why I'm saying out of the board too, right? Or do we have to review the whole right-hand rule for spinny things? But I'm going to use the right-hand rule in indicating the direction of spin. So if you'll recall, we have a choice. It's either spinning in such a way that it's spinning out of the board or into the board, right? Because this is the plane of the board. So your fingers curling this way points your thumb out of the board. Your fingers curling this way points your thumb into the board. The direction of spin is this way. So we say that the direction of spin will be out of the board. That is our positive direction, out of the board. Okay, we're going to need that because we're going to be calculating torques in a bit. And we have to be careful about whether those torques are positive or negative. Yes, ma'am?
Isn't there like a symbol for if it was out?
There is. And the symbol for out of the board is a circle with a dot in it. I would put that right on the center and say that's my direction out of the board, that's the direction of spin, but I know the green's kind of hard to see. So, are we good to get started on this? Dynamics questions have two parts. They have force parts, which we are familiar with doing. But they're also now going to have torque parts. Oops, why did I put 0 there? I'm sorry. They have force parts, which we are familiar with doing, and they have torque parts, which we are less familiar with doing. This is a system in which the net force is not going to be 0. It's going to be equal to ma. So applying that to each object is going to experience an unbalanced force and will accelerate. Now, I don't believe the wheel is going to have a translational acceleration. So the pulley, I'm going to state, has no translational acceleration. It's not changing location. Everybody follow along? Because they will ask questions about the forces acting on the wheel. And currently, there's huge misconception probably about the forces acting on the wheel. So let's focus on the boxes for a minute. I think all of you agree that the box on the right is going to go upwards. That makes sense? So we could argue that the forces it will experience will be tension minus weight. It's going to equal ma. We did this yesterday. And the box on the left, it too is going to experience an unbalanced force. I think we all agree the box on the left is going to go downwards. So we said downwards is positive. 2mg minus tension equals 2ma. Now, raise your hand if you believe the wheel is going to spin. So about 2/3 of you. It's disappointing because I'm hoping all of you realize we set the spin direction to be positive because we all think the wheel is going to spin. You understand why asking that and not seeing the results could be bothersome? I think the wheel is going to spin. I think the wheel is going to accelerate. You'll have an angular acceleration. Now, this is the part that I want to be very careful about. These two tensions can't be the same. And it has to do with the wheel. Let's just isolate problems. We have to be aware of that. So this tension on the right is different than this tension on the left. In our prior example, we just assumed they were the same because we said our wheel had no inertia. And in a system where the wheel has no or very little inertia, the tensions are the same. But in the real world, it takes unbalanced torque to get the wheel to move. This creates the condition for unbalanced tensions. Now, looking at the wheel here, our old way of solving this problem can't be used. Do you notice why? There's no way to eliminate the two tensions to find the acceleration of the system because the two tensions are different. You will not be able to solve the problem with tension alone. You will have to use torque. In fact, it will be your torque equation that brings the left and right side of these problems together. I'll say it again. It's going to be your torque equation that's going to bring the different parts of your problem together. All right. We identified the forces acting in our system and identified them for each mass and built a force equation for each mass. We identified our object was a composite object and calculated the moment of inertia for the object. This system is the motion of this mass connected with how far the wheel will turn. Are they connected together? And does it make reasonable sense that you could use this set of relationships for how they're related? Does one rotation of the wheel result in one change in displacement? That's a circumference. If this goes, remember, before we'd ask, if this goes up a meter, does this go down a meter? Now you have to ask, if this goes up a meter, does this go down a meter, and does the outside edge of this turn a meter? If it does, then you can use this. Ours are going to use this. This is what we're going to do. We're not going to try and mess with this too much. But believe it or not, maybe ask you to prove that the moment of inertia of the system was 5/3 mr squared. And maybe give you that one, because obviously the 5/3 mr squared plays a role several other times. But no, this is not the kind of problem where they'd likely give you the answer at the end. All right, so I have a couple of questions. First, Chris, go ahead. For just a minute, and think about only the wheel. So here's just the wheel. Wait just a second, I'm trying to be consistent. Oops, that's not being consistent. All right, so the wheel has inertia. We think it's going to accelerate this way. Now, not unreasonable, but the only way it can accelerate in that direction is if it's experiencing an unbalanced torque in that direction. There are three forces acting on the wheel. You may not know all of them, but I think you can name two of them. Tension here and tension here. We know those are acting on the wheel because the string is wrapped around the wheel, so therefore there's a tension on either side. There's another force acting on the wheel. Where is that other force? Oh, sadness. Sadness, really? If these are the only two forces, it falls down, right? What keeps it from falling down? Yeah, there's got to be something acting upwards on it. What's a likely thing that could be acting upwards on it? I mean, I'm not trying to make this hard. Don't overthink it. This is the wheel. And there's something pulling down on both sides. Well, what would be holding it up right now? Me? Yeah. So if I'm saying that the wheel is mounted someplace, there's got to be a mount. Would you agree that that's probably acting at the center? Yeah. Okay, so I think something's acting at the center. Wherever the pivot is, I think there's something pushing up on the wheel at the center. And it's got to be enough to keep the wheel from falling. I don't know what you want to call this. A normal force, the force from the mount, F, I don't care. There's something's holding the wheel up. And it's got to be big enough to deal with the fact that there's two forces pulling down. Now here's the clincher, the important thing. That force at the center doesn't apply a torque because it's at the pivot point. Our systems that are dynamic have to have a functional pivot, something that I can actually twist about. You need to be aware of the pivot point from now on. Unlike with static problems where you can set any point to be the pivot, you can't in dynamic problems. They have to have a clear pivot. The only way this system accelerates is if the torques are unbalanced. Now that tells me something. I hope it tells you something. It tells me that this torque on this side has got to be bigger than the torque on the other side. It's the only way this system will accelerate, is if the torque on the left is bigger than the torque on the right. So those two tensions are no longer the same. Again, net force equals 0 on the wheel. It's not accelerating by changing location. This upward force minus tension left minus tension right equals 0. It is not an uncommon question to be asked to figure out the force that is holding your system upwards. So it's not uncommon to be asked to find this. So just be prepared for it. Now, let's deal with the torque here. Let's not look at what we have sitting over there. Let's deal with the torque here. A brief reminder. Torque is equal to R cross F, which is R times F times the sine of the angle between them. Okay? Just keeping that in the back of our mind because we are going to be calculating torques. In this system, we think the torque is going to be is going to cause something to move with an acceleration out of the board. So we're going to start from the standpoint that the net torque equals I alpha. Let's see. We spent some time finding out what I is. So we already have that. It's tucked away. We have to find a way of expressing the torques here, and I see two torques acting in the system. I see a torque due to the force of tension on the left side of the wheel, and I see a torque due to the force of tension on the right side of the wheel. So let's start by remembering that each torque is going to have the same format. So over here on the side, because I try to be explicit, you can skip these steps if you know what to do, but I'm going to try and be explicit. I'm going to write out each torque. I'm going to write out the torque on the left and the torque on the right. And then I'll put them together in just a minute. The torque on the left has two parts. It's going to have R, which is the torque arm length. I hope that you can all see that this has to be the torque arm length. And it's the radius of the pulley. It's not a surprise. That's why we use pulleys. Radius shows up a lot. So I'm going to say that the torque arm length is R. The size of the force is TL. And this will be true of all pulleys. All pulleys will have a force that acts perpendicular to the torque arm. All of them. It's a circle. So if you try to pull the string at a different angle, it just unwraps until it's, again, a tangent. So all pulleys will have a 90-degree angle as part of their torque calculation. It makes it nice and easy. Direction, R cross F. So using the right-hand rule, that torque is positive. Got to do this torque. Let's do its direction next. Right-hand rule, I point my pointer finger in the direction of the radius, rotate my finger until it's in the direction of the tension, which is downwards, and my thumb points into the board. So this torque has to be negative because it's into the board. Trying to be consistent, I think this works out okay. Now, I do want to remind you, out of the board and into the board is arbitrary for positive and negative. Does everybody understand that too? It's just like saying up can be negative sometimes. You set and you decide. But we have decided that this rotational direction was positive, so out of the board became our positive direction. Now, I think it's pretty clear, but I want to make sure I talk it all out, that the torque arm for this side will also be length R. That doesn't have to be true. I've given you some homework questions where it's not true, where there's an outer radius and an inner radius, and the string can be held on either side. So just be aware you can have gears as part of your problem. Anybody who's ridden a bicycle knows that bicycles have gears too. That's just changing the radius. The value for that torque arm is still the radius of the wheel, and we'll have TR sine 90 degrees. Good so far? Let's bring it all together. Net torque, RTL minus RTR equals 5/3 M R squared alpha. I just pulled all the pieces together. Now, this just quick. We then isolated the spinny part of the object, spinny part of our system, and isolated the torques that are causing it to rotate. If we bring all the pieces together that we have this for torque. We have 2mg minus TL equals 2ma for the mass on the right. And we have TR minus mg equals ma for the mass on the right. So this is the mass on the left, that one's the mass on the right. Now, this is a whole lot of stuff. And our job is trying to figure out the same thing we figured out before. How does our system accelerate? Do you notice that we've got a problem a bit? It might not seem like a problem right off, but we do have a bit of a problem. If we're trying to figure out the acceleration, well, we have two different accelerations here. In the past, we could just add these things up. And that's what we did when we did this problem yesterday without a massive pulley, right? We just added these two things together, and they both had A in it, and we didn't care. We don't have that now. So it's at this moment you need to ask yourself a question. Is there a relationship between the acceleration of the masses and the angular acceleration of the wheel? Now, don't take this lightly. If there's going to be wiggle room in trying to make you second guess or double guess what's going on, it's going to be here. I don't want you to make too much of it, but what you have to ask yourself is, for every AP question that uses this, you get a point for the proper substitution, for seeing that you can substitute for alpha A over R. In this case, it's capital R, because that's the radius of the pulley. So now we do that. We put in that relationship. So RTL minus RTR equals 5/3 MR squared times A over R. This substitution is what makes our problem work. Let's just record this for posterity. Chris asked why we got rid of, or how we got the sine of 90 degrees. Getting rid of the sine of 90 is easy because it's 1. But how do we get 90 degrees? Well, looking at this picture kind of tells me that's 90 degrees. But also what I said was for any pulley, and you should put this in your notes, Chris. If I tried to pull at a different angle, the string would just unwrap until it was tangent to the circle. And therefore, the string will always be tangent to the circle and therefore perpendicular to the torque arm. This will be true for any round pulley system in which you are applying a torque. Now, I said round, right? This would not be true if it were elliptical or something like that. This only works under this circumstance. But that's why we use round stuff. Okay. I wanted to get to this part because do you notice all the R's cancel out? I mean, do you? I hope you do. And let's make sure everybody's with this. This R cancels right here with that one. And then I have an R here, an R here, and an R here. That's an R in every term. This happens purposeful in this way. This kind of problem is done like this on purpose in not just physics, but in real life, because if you're careful, you can get the R to cancel out. And what you're left with is another relationship that's like a force relationship for the object that is spinning. And now you actually have something that you can use. Bring in these other two things, 2mgtl, not TL. Sorry, I got all flustered. Minus TL equals 2mg. Oops, one more. And I said 2mg, but it's supposed to be 2ma, sorry. I got all flustered. I was all on a roll and lost it. And then TR minus mg equals ma. Once all the R's cancel, we now have something that we can add together. Again, right? This becomes kind of the nucleus. It has both tensions in it. So if you're going to do substitution, you sub into your torque equation. If you're not going to do substitution, like I'm not going to do substitution, I'm going to recognize that there's a positive TL and a negative TL, and a positive TR and a negative TR. So I'm just going to add the equations down, knowing all the tensions cancel. And when I do, I'll get 2mg minus mg. And on this side, I'm going to get 5/3 ma plus 2ma plus ma. Everybody check the algebra? We all good? Is everybody good? I'm just trying to make eyes with everybody and make sure everybody feels the same way. I think some people are not good.
Wouldn't the F for 5/3 be like capitalized?
Did I make this a different M than the others, or is it saying, okay, so if it's different M, if it's capital M, that's fine. It's not really going to affect the answer. So, do you see something? You may not. Factor out the A. And leave this as a difference for just a minute. This is net force. It was the two things that were added to the pulley. It's the weight on one side and the weight on the other. This is the inertia of the system. Our combined object, that 5/3 m, becomes the inertia of the system. It's how it contributes to this system. The wheel actually has a mass of 3m, right? Both bars were m, the ring was m. So the whole mass of the wheel itself is 3m, but its entire mass doesn't contribute. Only 5/3 of the mass does. Because the whole thing was 3m, so it's much less than that. A much smaller amount of mass actually contributes to the total inertia that it applies to the system, but it adds something to that inertia. You remember what our original answer was before we did this, right? When we did the problem yesterday, and we found the acceleration without the wheel, we found that the answer was going to be 1/3 g. Do you remember that? Which, if you back up just a bit, the acceleration was mg divided by 3m, because 3m was the total inertia of the system. Well, this time we're going to have mg, and that's going to equal all this stuff, 5/3 m plus 3m times a. That makes the acceleration with the wheel mg on top and 5/3 big M plus 3m on the bottom. Now, I know this is a lot, and I was trying to be very slow, very deliberate. Our object accelerates slower because the wheel is now playing a role. Our wheel makes it more difficult for the system to accelerate. Therefore, we get this contribution to its inertia in the denominator there. So it accelerates slower because of that. Shouldn't be a surprise, but this is how torque plays a role in adding inertia to our systems. Now, it's a lot to get there. I don't in any way minimize how much more has to be done here. But do you see that it's very similar to what we did before? But there's a lot of steps here. I don't want to make it seem like it's easy. I tended to blow through this stuff without being careful. So I took, like an entire, should they be the same? Meaning if everything had been multiples of m, then yeah, you would go one more step. You would add those together. 5/3 and 3/3 is going to be, let's see, that's 9/3. 9 and 5 is 14/3. So this would be mg over 14/3 m. You would cancel the m's out, and you would get 3/14 g. Now, comparing it to yesterday, yesterday's was 1/3 g. 3/14, less than a third. So it accelerates slower. Not a surprise. The inertia prevents it from accelerating as fast as it would. Yes, ma'am.
So with this one of the problems, did they give you the answer and you have to prove it?
Oh, no, probably not. No. This would likely be a problem where they would expect you to do all of this without knowing what the answer is. They would